All right, so let's review what we did last time. Last time we defined a Bordism category with geometric structure. And let's see how that went. We defined a d-dimensional geometric structure. Well, first we talked about the case without smooth families. And in that case, a d-dimensional structure is something defined on smooth D-manifolds that we can restrict along open embeddings. And this naturally leads to a definition that a d-dimensional geometric structure is an infinity sheaf of simplicial sets, or infinity groupoids if you prefer, on the side of d-dimensional manifolds and open embeddings. So a geometric structure can be defined on any d-dimensional manifold. It can be restricted along open embeddings, and you can glue, if you have an open cover of a D-manifold by some open subsets, and each one is equipped with a geometric structure, you can glue them together to a geometric structure on the union. Then we saw a whole bunch of examples like Riemannian metrics, various differential geometric structures like conformal, symplectic, compact, complex, Kähler structures, Calabi-Yau structures, various Riemannian metrics with restriction on curvature, positive, negative, could be a sectional, scalar, Ricci curvature. Another example, very important one, is when your Bordism, when your manifold is equipped with a smooth map to a fixed target manifold. That's known as a sigma model in physics. It's, in mathematics, it's also responsible for Bordism categories modeling parallel transport in principal G bundles, vector bundles, bundle gerbs. All these have a notion of a parallel transport. Traditional topological structures like orientation, spin, spin C, and whatever framing, all are examples. And of course, in physics, you also have gauge fields and higher gauge fields. Ordinary gauge fields, and that's an example where you no longer have a sheaf of sets, but rather groupoids, which groupoids can be converted to simplicial sets using the nerve functor. And one typical example would be when you send a smooth manifold to the groupoid of principal G bundles with connection over this manifold, and morphisms are connection-preserving isomorphisms. Higher gauge fields are defined analogously but using bundle gerbs with connection, like for B fields or C fields. C fields need bundle 2 gerbs, or even more sophisticated things like infinity groupoids of differential co-cycles for differential K-theory, model Ramon-Ramon fields in string theory. And then, since we already discussed how we want our functorial field series to map smooth families of Bordisms to smooth families of values, we discussed how to modify this definition to account for such smooth families. And this is basically done by modifying the site of d-dimensional manifolds and their embeddings into a site that is fibered over Cartesian spaces. And here I did say Cartesian spaces, but just for the future's sake, let me also point out that this Cartesian space U can in fact be something more general. Examples include, let me write it here. Examples include, so I guess that's what we're calling our paper ST card. Let me write it here. ST card is, well, you can find a formal definition in the paper, but let me just give you some examples. Ordinary Cartesian spaces, super Cartesian spaces, so these are super manifolds isomorphic to R, P, bar, Q, as used in supergeometry and supersymmetry and whatever. Other examples include various sites used in infinitesimal analysis. For example, you can take various categories of C-infinity loci, well, Cartesian. For example, take Rn times the spectrum of a Weil algebra. And perhaps I should also mention derived Cartesian spaces. So these are defined through the differential graded algebra of functions, which will be simply the symmetric C-infinity algebra on some, let's say, finite dimensional chain complex, concentrated in finitely many degrees. Let me put it like this. So the reason I mentioned all of this is the setup is general enough to handle not just families, smooth families in the usual sense, but also smooth families as you want them in supergeometry, derived geometry, infinitesimal analysis, smooth infinitesimal analysis. So the formal definition you can find in the paper. Let me just, of course, the Cartesian spaces will be our main example, which already illustrates much of what is there to know. So this U here, U in principle can come from this category ST card. Okay. And so what you do is you recast everything in terms of smooth families over U. For example, instead of a d-dimensional manifold as an object, you now have a smooth family of d-dimensional manifolds. That's simply a submersion over U. And likewise, morphisms now will be, well, first you have a map of base spaces, which is an arbitrary smooth map, a morphism. And then the map on total spaces must be a fiber-wise open embedding. So that means in a naive setting, it just means for any point in capital U, the induced map of fibers is an open embedding. All right, so let me also mention, just in case you are wondering how this is going to work in the more general categories, like here, all those more generalized notions. A submersion could be defined as a morphism that locally in M and U looks like a projection of the form R d times U over U. So that's a typical example of a submersion with d-dimensional fibers, and you simply require that locally in the source and target, your submersion looks like this projection map. And likewise, the condition that you have a fiber-wise open embedding, you must recast it in a slightly different way. What you do is you pull back the submersion N over V along G, you pull it back. Now you have a submersion over U So you have this pullback map. So P is a pullback. This map P over U is a submersion. You have an induced map from M to P, which is an induced map into the pullback. And look at this map from M to P, that must be an open embedding in the usual sense. So pulling back is a trick that allows you to replace talking about fiber-wise open embeddings. When you pull it back to the same base, the fiber-wise open embedding becomes an ordinary open embedding. Okay, and we also define a quadratic topology where a family of maps is a covering family if on the base spaces you have some open embeddings, and on the total spaces you have open embeddings that form a covering family. So on the total space you want a covering family. And then the definition of a geometric structure will now be exactly the same as before, but using the family version of your site. And we discussed how the previous examples can all be recast into this new setting. Basically, all of them are done in a very similar fashion. The differential geometric constructs like the tangent bundle or the cotangent bundle are replaced by the appropriate family version, which is known as the vertical tangent bundle or the relative tangent bundle. This is simply defined as the kernel of the induced tangent map on the submersion. So everything is done now fiber-wise using vertical tangent bundles. This includes, for example, topological structures like orientations and framings that will now be fiber-wise orientations and fiber-wise framings. Okay, and then finally we define boardism. Let me keep this here just for your reference. We finally define boardism categories with geometric structures. This definition relies on the previous definition of boardism categories without geometric structures. So what we did here, we simply declare that the boardism category will be a smooth, and here I guess I should really say ST card now. Oh, ST, by the way, stands for structured. I should have mentioned. It's not a perfectly good name, I guess, but structured. It simply refers to the fact that superstructure or derived structure is an additional structure on a Cartesian space. So you have a smooth, symmetric monoidal, infinity D category, and the simplicial set for any such combination of objects is defined as a diagonal of the nerve of a simplicial category. And we have to define separately objects and morphisms of this simplicial category. And objects will be a disjoint union over all triples MPC. These are just objects corresponding in the usual boardism category without geometric structure. So this will be an ambient manifold, a partition into disjoint components for the gamma structure, and a collection of cut tuples, which we call a cut grid, which is what partitions your boardism into elementary cells. And then for such an object, you evaluate your geometric structure on the trivial family of smooth manifolds given by the projection of M over U onto U. So it's a trivial family with fiber M parameterized by U. So when we evaluate on some object U, that means we are doing everything in families over U. And here is exactly what you can see. And likewise, the simplicial set of morphisms was defined as a disjoint union over all morphisms F in the Bordism category without geometric structure. So this is objects of board D evaluated on L. Sorry. Oops. Let's see. Annoying thing about the eraser is. Oh, and this one crashes. Yeah, I should not use this one. I got crashes from it last time. And likewise, here you get morphisms in this Bordism category without geometric structures. And you evaluate your geometric structure on the target manifold. Now, to define the sourcing target map, the target map will be simply a projection. It will simply take the summand and include it as a corresponding summand in objects, whereas the source map will pull back. It will pull back along the open embedding F. So recall that morphism F in the previously was defined, let's see, somewhere here. Yeah, right around here it was defined as an open embedding of M into M prime here. And you can pull back along such an open embedding, and this will be the target map. Okay, so that was a review of what we did last time. And today I would like to make the final step and define isocopies of Bordisms, but perhaps it's a good idea first to ask if there are any questions about the previous definitions first. All right, let me now explain why we want to, as if the definition wasn't already complicated enough, we still have to make it even more complicated, and why is that necessary? Well, the motivation is actually really simple. We, for the purposes of proving something like the cobordism hypothesis, we need a way to express the fact that bordisms are dualizable. Every bordism has a dual in the infinity D category of bordisms. And let me actually ask a question before we move on. How many of you guys are familiar with dualizability of objects and morphisms in symmetric monoidal categories or higher categories? Okay, one is familiar, or two maybe are. Okay, anybody else? What I'm asking is how much of a review I should offer right now, or should I just proceed directly to explaining the Bordism category case? Any opinion from the other three guys, Arshak and Misha and Igor?
I think we may provide discussion without descending to some general definitions.
You mean it's not necessary, you mean, right?
Yeah,
Okay, okay. Yeah, so let me just explain it in this particular case then only. So what does it mean, say, for a morphism, a Bordism? Imagine the simplest possible case, uh, the case of a one-dimensional Bordism. So that's just an interval, And let's say we have Riemannian metrics, for example, on our Bordism. So this interval has length t is greater than 0. Well, what does it mean to be for this Bordism to be dualizable? Well, let's recall that a dual morphism goes in the opposite direction. If this was a Bordism from A to B, then the dual Bordism has to go from B to A. And here I drew a picture for you how such a dual Bordism would be constructed. What you do in general to construct the dual Bordism is you take the original Bordism here, and at the endpoints you will attach the unit and co-unit of the source and target object respectively. So here you have, I guess, the co-unit of the target. Here you have the unit of the source. And the effect of this attachment or gluing is that what used to be the target is now the source. Notice how the direction of source and target reversed here because of this gluing. Likewise, what used to be the source is now the target. So this gluing Bordism at least has a correct source and target. And now you say, well, okay, in order to be a dualizable Bordism, or in this case, we actually want an interval to be invertible Bordism. After we glue them together in a single sort of interval, we expect to get something like identity. But if you imagine gluing these two intervals together, what will happen is that we will have one interval of length t greater than 0, another interval of length t greater than 0, and the length of the resulting interval will be positive. And it's not at all clear why this should be identity. So we somehow need a mechanism that would allow us to say that this composition is in some sense maybe not equal to, but homotropic to identity. So more generally, if you imagine doing this for higher dimensional Bordisms, perhaps you want cylinders on Bordisms to be invertible, but that means a cylinder of length t greater than 0 should be in the same connected component as a cylinder of length 0. And I'm sort of somewhat vague with what connected component means right now, but we'll see in more detail what it means in a few minutes. So of course, this homotropy I mentioned is what will ultimately be called an isotropy of Bordisms. This is just a name or a new term to make it different from the previous notions of homotropy and concordance that we already had. Let me recall maybe that in any simplicial set, you have a notion of a simplicial homotopy. And that's what we call homotopy in general. But also, if you have a pre-sheaf on Cartesian spaces, then by looking at the real line in Cartesian spaces is also responsible for implementing a notion of homotopy, which is what we can call concordance. So this notion is going to be different from these two, and that's what necessitates a choice of a new terminology, isotopy. So the idea is that isotropies of Bordisms in general can move cuts inside your ambient Bordism. And we'll see how this works maybe in this example, but let me give you a formal definition first. So first, we'll need one more final change in the formalism. We'll need to replace, and I promise this is the last one actually, so there will be no more changes. What we will now see will be actually the final definition as it is actually used in geometric cobordism hypothesis. So what we need to do, and strictly speaking, this is not absolutely necessary, but it does make it more clear, I would say, what's going on. We need to replace simplicial sets, this model category of simplicial sets equipped with a Conquillian model structure, with the model category of smooth simplicial sets, so the smooth part will ultimately be responsible for controlling isotropies. Let me now also point out a potential source of confusion. Now we in principle have two different copies of Cartesian spaces in the game. One is Cartesian spaces that are structured Cartesian spaces, and these control smooth families, and I should also say probably concordances. Whereas smooth simplicial sets, by definition, are pre-sheaves of simplicial sets on the Cartesian side. These are ordinary Cartesian spaces. We don't really need much more than ordinary Cartesian spaces at this point. And these control isotropies. So it's important not to confuse the two. So isotropies and concordances are not the same. And this model category will be equipped with a with a model structure. And this model structure will be transferred from simplicial sets. So simplicial sets are equipped with a Conquillian model structure, the usual model structure. And as we discussed previously, if you have a right adjoint functor, which in our case will be what is called a smooth singular complex functor, which sends a pre-sheaf f to the diagonal of the simplicial object in simplicial sets that sends a simplex n to the value of f at the smooth manifold delta n. So this is the extended smooth simplex, so that's just a Cartesian space Rn. And the diagonal means you evaluate it on delta n, and then you check n simplices here. Sometimes the weak equivalences that you transfer in this manner on these pre-sheaves are known as shape equivalences. They should not be confused with Czech equivalences. So these form a strict superset of Czech equivalences that we previously discussed. So any Czech equivalence is a shape equivalence, but there are many more shape equivalences that are not Czech equivalences. And the easiest example would be take the map from Rn as a smooth manifold to a point. This map is a shape equivalence because the shape of Rn and the shape of a point are both contractible simplicial sets. But in the Czech model structure, of course, the smooth manifold Rn is not diffeomorphic to a point, so they will be different. And it's a theorem you can prove, and I guess, well, you can find a proof in my paper called Projective Model Structure on Giffey-logical spaces and whatever. But it's a theorem that this functor becomes a Quillen equivalence. Let me put it over tilde. Tilde means you have a Quillen equivalence. So, and that's why I said ultimately that the use of smooth simplicial sets here is optional, because the model category of smooth simplicial sets is equivalent to the model category of simplicial sets with conquillen equivalences via the smooth singular complex functor. So in principle, I don't really need this here. I could have used simplicial sets, but as you will see in a second, keeping not mixing the two directions, the Cartesian and simplicial direction, together is kind of makes things more clear. All right, so with those preliminary definitions out of the way, we are now ready to define, and here I guess I use a bold B to refer to the enriched. So bold means enriched. I mean, I write bold, but in the paper it's actually a Fraktur script, and that means enriched. Enriched over smooth sets or smooth simplicial sets. So that means simplicial sets, but replaced by smooth simplicial sets. Okay, so but otherwise the formal structure will be exactly the same as before. We are once again defining such a functor. Its value on some u, l, and m1 to md will be encoding the now what is smooth simplicial set of U families of Bordisms partitioned into L components with a cut grid having this many cells in each direction. So it's the same as before, but now instead of an ordinary simplicial set, you have a smooth simplicial set. And the value of this smooth simplicial set is some Cartesian space L. Will be encoding the simplicial set of isotropies parameterized by L. Let me compress. And you can see how the definition works. You literally take the usual, the previous construction of the Bordism category, which was giving to you right here. Yes, the ordinary Bordism category is a smooth hierarchy category. And instead of U families, you now have U times L families. This definition may seem basically almost tautological to you, like why bother with such a triviality? Like I now have two parameters U and L, but the only way we use them is by combining them together and looking at this family parameterized by both U and L. So what's the point? Well, the point is that in a second we will introduce the Bordism category with enriched Bordism category with geometric structures and isocopies, and there L will no longer be participating just formally. It will actually have its own separate role. But for now, if you don't have a geometric structure, then yes, the Bordism category without geometric structure, but with isocopies, all what it does, it allows you to sort of have a family of Bordisms parameterized by a Cartesian space instead of just a single Bordism. But this already has consequences, by the way, of its own, and let me maybe just give you one example. Let me give you maybe the simplest possible example. See, I hope I can squeeze one more line here. But let's hope this all works out as expected. Okay. Maybe I can squeeze one even more lines. Let's see. I hope I can do this rectangular select. Okay, and now I want to rescale this. Yep. Yeah. Oops, I'm very sorry. Oops. Sorry about that. Let me let's see, where were we? Example. A single example that illustrates what's new. And let me just take the d equals 1. And let's look at the say, I don't know, one-dimensional Bordisms. These are just, say, for example, intervals. And a priori, previously, we had two different types of intervals. We had an interval which was degenerate. Let me kind of depict it like 2 points at the same location, degenerate interval. And we also had intervals where the source and target were at different locations, so non-degenerate. And these were different Bordisms. In the previous Bordism category, there was no sort of isomorphism between them. In principle, a functorial field theory can assign completely different values to a degenerate Bordism, which is identity. So that always goes to identity. And the non-degenerate Bordism you could have sent to any other morphism. For example, if you considered the category of values being the category of vector spaces, vector spaces, you can say, okay, a point maps to some vector space V. A degenerate morphism would have to map necessarily to identity on V, but a non-degenerate Bordism would have to map to any morphism E from V to V. And the only other property we require here is that since this is a functorial field theory, the composition of this interval with itself is again diffeomorphic to an interval, right? So if you glue two intervals, two non-degenerate intervals together, you get another non-degenerate interval which is isomorphic to them, diffeomorphic to them. So E composed with E equals E. So the non-degenerate interval would have to map to some eigenpotent element which need not be even invertible. So E could be non-invertible. Let's see now what the introduction of isotropies gives you. So we have, if we take, okay, and now you get even a bit more space. Let me actually, let's see if I can do this trick one more time. Yeah, this software is pretty good, even though it crashes easily, unfortunately. So now, let's see how everything changes when we click, when we pass the setting with isotropies. And we click, say, L equals real numbers. Then all of a sudden, where previously we only had a discrete simplicial set of intervals, which basically had two connected components, one connected component for a degenerate interval, and another connected component for the non-degenerate interval. So they were not isomorphic previously, because there is no isomorphism that, or diffeomorphism from an interval of a non-trivial length to a degenerate interval. But now we have a whole smooth family parameterized by the real numbers, and it looks like this, right? So here is L, and here is your family. The 2 points are pulled apart. And at this point, it's a degenerate interval. And at any other point, it will be non-degenerate. So now you see the degenerate interval and the non-degenerate interval are in the same smooth family. And so the practical implication of this is that now, since the Bordisms are in the same smooth family, their values, identity and E, must also be in the same smooth family. Let me put it here. So identity and E are in a smooth family. And furthermore, this smooth family, if you look at this picture, you see at some point you have identity, and then immediately after you have a non-degenerate interval. So that means you have a smooth family of linear maps where at some point you have the identity map, and immediately after you have E. But invertible linear maps form an open subset of all linear maps. So the fact that the fact that E occurs arbitrarily close to the identity map means E must be invertible. So E is forced to be invertible. And this is something that was previously simply not present. Like it was perfectly possible to construct a functorial field theory that would assign something non-invertible to E, to a non-degenerate interval. Yeah. So that's one practical consequence of the existence of isotropies. And we'll see more practical consequences in a few minutes. But let me first explain how everything is generalized to geometric structures. And before I do that, let me see if there are any questions so far.
Please may you comment a bit more about C infinity simplicial sets, about some physical intuition behind all this. On the
Well,
right
the
hand.
point to make here is that previously we had a simplicial set. Well, the easiest examples of simplicial sets are, say, nerves of groupoids. And now what we are basically saying is it's a nerve of a smooth groupoid. For example, a Lie groupoid. So where previously we had just an ordinary groupoid, now we have a Lie groupoid, or perhaps an infinite dimensional Lie groupoid, which is important, for example, when you're encoding, say, I don't know, gauge fields, right? In gauge fields, your structure group is a Lie group, which is not a discrete Lie group. It's something like U1 or SU2 or SU3. These are non-discrete Lie groups, and so they have a non-trivial smooth structure. So when you start encoding gauge fields, we will see we need some kind of not just a groupoid, but a Lie groupoid. So that's one point maybe, is that such smooth structures are naturally present in physics settings, gauge fields and the like. And the other thing, of course, is that the point of this C infinity simplicial set is that that's precisely how you encode isotropies. So the fact that you have this smooth family here is precisely allowed by the fact that you have a smooth simplicial set here. It's not possible to talk about smooth families in an ordinary simplicial set. So that's the point of the construction. All right, let me now explain how everything is generalized to geometric structures. And this is basically the final step to define the ultimate Bordism category, well, ultimate at least for the purposes of our papers so far. Of course, there are more bells and whistles you can attach to a Bordism category, like defects. Defects is something you want in physics very much so, and this will be a subject of a future paper, which is not yet ready. But for now, let's concentrate on the simple case Bordisms without defects. All right, so how exactly do we generalize everything to the setting with geometric structures? Well, the definition of the geometric structure itself now has to be also appropriately enriched over smooth sets or smooth simplicial sets. And so what happens is you modify the definition of the original site, FemD. Recall that FemD used to be here. It's a site of smooth families of D manifolds, with morphisms being fiber-wise open embeddings. And now we define an enriched version of that. The enriched version has exactly the same objects as before. The objects are exactly the same as before. Maybe I should write it down. Objects, same as in FemD. But morphisms now will, instead of forming a set, as I did before, morphisms now will form a smooth set. So this is a category or a site enriched in smooth sets, pre-sheaves of sets on the Cartesian side. So instead of specifying just a set of morphisms, which was just a set of such commutative squares here, with f and g being the data of a morphism, now I have to specify a smooth set of morphisms. So given any Cartesian space L, I have to specify what it means to have an L family of morphisms from one object, T over U, to another object, T prime over U prime. And here is a definition. Such as set of morphisms is precisely the set of morphisms in the usual category, non-enriched, where you add a product with L to your base space and to your total space. So the source is now comes in as a trivial bundle over L, so to say. So for every point of L, you will have a, if you restrict to this point, you will see a morphism from T over U to T prime over U prime. And that's what it means to have an L family of morphisms in this site. Let me also emphasize at this point that the bottom map, the map on base spaces, is required to be, well, I should phrase it a bit more carefully here, so let me not write proj right away. So this bottom map must be the composition of the projection map from U times L to U, and then some map from U to U prime. So this is a projection map. So that means you are not allowed to have a non-trivial dependency on L in the map of the base spaces. So the only thing, moving around capital L, you are allowed to change the individual fiber-wise embeddings, but you're not allowed to change the map of the base spaces. So the map of the base spaces is fixed. It's fixed in the entire family. It never changes. The only thing that changes are the actual fiber-wise open embeddings. So in this language here, G stays fixed, but the individual open embeddings are allowed to move around smoothly. So that's that's the point of this definition, that the open embeddings themselves are allowed to move, but their domain and codomain stays fixed. So G of U never changes in families, so never changes. So you always rank the same NGU, and it's just this map, the open embeddings, that can change. Okay, so that's how the psych FMD is going into a psych enriched in smooth sets. And now we can define an enriched geometric structure as an enriched presheaf, meaning an enriched functor from the opposite category of FMD to smooth simplicial sets. And this functor, as before, is required to be an infinity sheaf. So what is the meaning of an enriched geometric structure? The meaning of an enriched geometric structure is that in simple terms, previously a geometric structure was something that was defined on any d-dimensional manifold. And a bit more generally, it was defined on a smooth family of d-dimensional manifolds. And furthermore, you could restrict such a structure to a smaller open subset. And the infinity sheaf property also allows you to glue such a structure from some open cover. And now you have one more operation, which is if you have you are allowed to pull back a geometric structure not just along an individual open embedding, but you are allowed to pull it back along a smooth family of open embeddings parameterized by some Cartesian space L. And such a pullback produces a smooth family in the category of in the target category. So instead of pulling back along a single open embedding, you are now allowed to pull back along a smooth family of open embeddings. And you get a smooth family as a result. Smooth family of maps of smooth simplicial sets. All right. Any questions so far? Okay, we are now basically ready to move on to our final definition. The enriched Bordism category with geometric structure and isotropies. Maybe I should have said this. So the input data to the construction is a dimension D, and now an enriched geometric structure. Oops, I'm not sure why I wrote this here. Enriched geometric structure, and we are now going to construct the enriched D-dimensional Bordism category with a geometric structure S. It will be a functor from, so it's a smooth symmetric monoidal infinity D category, and it's enriched over smooth simplicial sets. And as before, I'm actually going to lang not directly in smooth simplicial sets, but rather I'm going to lang inside smooth simplicial categories, to which I'm then going to apply the diagonal of the nerve as before. So this functor is defined exactly the same as before, but now in sheaves or pre-sheaves over Cartesian spaces. And the actual definition is pretty much exactly the same as we did in the last lecture. The construction is basically exactly the same, but now instead of evaluating an ordinary geometric structure, you will evaluate an enriched geometric structure. So as before, we take as the so in a smooth simplicial category, you have a smooth simplicial set of objects, which will be a disjoint union over all objects in the ordinary. So this is a bold B, by the way, which we defined previously. Well, it was just in the previous page. This bold B. And for every such object, we take a smooth set given by evaluating the enriched geometric structure on the Bordism. So this smooth set can be evaluated at any Cartesian space L. So I guess strictly speaking, this is not objects, but rather objects evaluated at L, where L is a parameter controlling the smooth simplicial set. And just to remind you, as before, you can now see clearly that L and U play a different role. Which perhaps can be most easily seen with an example. Let me actually give you an example at this point so it's more clear why these things are completely different. And I should probably move this to the next page. Let me try to move this to the next page. Oh no. This is one of the points when it doesn't work so great. Let me try to do it again properly this time. Okay, so okay, perfect. how I deselect this stuff. Oh, all right. So here's an example which should really clarify the difference. And let me take the example of a sigma model. Where you fix X, let's say, a fixed target manifold, so that could be like the space-time, for example, or maybe something related to the space-time. Then the enriched geometric structure defined by such an X so I have to define, so let's define an enriched geometric structure corresponding to X. So this will be an enriched pre-sheaf. So that means, first of all, for any object T over U, I have to specify a smooth simplicial set. What is a smooth simplicial set? Well, a smooth simplicial set stands in any Cartesian space L to a simplicial set. In our case, the simplicial set will be an honest, ordinary set. No simplicial business anymore. And so what is a set? Well, it will be, let me maybe first write it down what it is in a more sort of conventional term. So it will be smooth functions from T times L to X with the following property. That, let's see, so the property is that for any, let me say it in the simplest way possible, for any point in capital U, the restricted map to the fiber of T over this point, so TU, which is a fiber of T over U, times L. There's this restricted map, which I'm going to denote by FU. This map factors, so FU factors through a d-dimensional manifold. So what this means is that the dimension of the fiber TU is equal to D. L can have any dimension. X can have any dimension. So it is quite a restriction that we require that this smooth map, in fact, factors as a composition through some manifold, let's say T, U, V, let's call it V, or W, actually. So W has dimension D, and we require that this FU factors through W. If this looks confusing, maybe you can also benefit from an alternative description, which doesn't give you exactly the same geometric structure, but it kind of gives you something that will ultimately give you the same answer. And so roughly speaking, this could be reformulated by saying that the rank of Fu is at most D. So this is not the same condition, but it roughly amounts to the same idea. Okay, so the takeaway from all of this is that both L and U allow you to deform some map from a d-dimensional manifold to your target X. But they allow you to deform it in a very different fashion. So imagine, for example, D equals 1. Then your typical fiber TU will be a one-dimensional interval. And this one-dimensional interval, well, if you deform it in the U direction, arbitrary deformations are allowed. So this is your ambient manifold X. So this is so the parameter space U will be, as you move around U, your paths will deform in an arbitrary way, totally arbitrary way in the space-time X. And the idea behind allowing such arbitrary deformations is that here, with respect to U, the Cartesian space, we are imposing the requirement that a smooth family of paths must map to a smooth family of values. So that's totally natural. L also encodes a smooth family, as we see, for example, in this definition, but it plays a very different role. L, it allows for a very restrictive types of deformations. So you have your paths, and now you see this homotopy, so to say, it must factor through a one-dimensional manifold. Or equivalently, the rank of this, well, not equivalently, but very closely related, the rank of this homotopy at any point must be at most 1. Which means, in particular, the picture I drew here is not going to work because the picture here, it deforms a path in a non-trivial fashion and it traverses some two-dimensional surface. So at a generic point, you will see a rank 2, not 1, because you are moving in the normal direction. So this map will have rank 2. So a homotopy of rank 1, this is basically known as a Singh homotopy or D-Singh homotopy. And it's kind of difficult to draw pictures, but let me draw maybe some, like what can happen to this path is that the types of deformations are allowed are very limited. And here is maybe an example of a deformed path. You start here, you go in the same path, and you will like go there and back again. Maybe go here, there, and back again. Do some stuff here. And ultimately, you move back to the same point. So you see, like we in this picture, we are not spanning a two-dimensional surface anymore because that's prohibited by this rank condition. But you are allowed to have rank at most 1, and such sort of deformations where you sort of grow out a tree, that's the only thing you can do. But as an important special case, imagine you have a loop that goes there and back again, like this. So you start at this point, you go in one direction, and then you go back using the same path. Then there is a homotopy of rank at most 1 that will contract this loop to a constant loop. What it does is that you will, at time t, you will go to some point here and back. And as t grows, you will traverse smaller and smaller distances, and eventually will scale at this point. All those paths are in fact the same path, but it's just an artifact of the picture that I have to draw them separately. So the kind of stuff you can accomplish with a single homotopy will be very limited. But it does give you something non-trivial, which is you can go there and back again, and you can contract this composition to an identity path. So that's something, that's useful. And so the idea, the physical idea, for example, behind this L family is that an L family encodes invariance properties of parallel transport. So in a gauge field theory, the parallel transport along a loop expresses basically the term you put inside the action functional. Sometimes these loops are known as Wilson loops. And parallel transport in general will not be invariant under arbitrary homotopies. Like a parallel transport will be invariant under arbitrary homotopies if and only if the connection is flat, meaning it has a zero curvature, which is a very restrictive condition. Whereas every principal G bundle has a parallel transport that is invariant under thin homotopies, which are very, very restrictive. So in particular, the fact that you can go there and back again, so like this, Musk is saying that if you parallel transport along some paths, and then you do a parallel transport along the inverse path back to the original point, then the resulting composition will be identity. And this property of parallel transport is captured by the fact that we do have a thin homotopy that takes this path, takes this loop that goes there and back again, and deforms it to the identity loop. So the isotropic direction in this case is capturing just a small part of the notion of a smooth family. It basically captures those types of deformations that do not really affect the action functional. So perhaps the physical meaning of these two parameter spaces is that the U space encodes the simple fact that a smooth family of Bordisms must map to a smooth family of values. Like, for example, in quantum mechanics, a smooth family of intervals of length t, where t is a smooth parameter, must map to a smooth family of time evolution operators, which is precisely what enables the existence of an infinitesimal generator, the Hamiltonian, in your quantum mechanical system. Whereas the L parameter, it basically will capture some very simple invariance properties of parallel transport. Like when you define electromagnetism, your gauge field in electromagnetism is a principal U1 bundle with connection, and this parallel transport in this U1 bundle will encode the Faraday action functional for electromagnetism, the Faraday-Maxwell action functional. This action functional will be invariant under such very special deformations of your loop. And this is what is encoded by the L direction.
May you revise a bit more about Bethin Gamatopy?
About what, sorry?
Diffin Gamatopy.
Yeah, so the definitions, the two different definitions, which are actually not quite equivalent but closely related, are given here. A desync homotopy, I mean, in general, let me maybe write somewhere here. Let me just an ordinary smooth homotopy between two maps from X to Y. So F and G are two smooth maps from, say, smooth manifolds X and Y. Then an ordinary smooth homotopy will be a map from X times 0, 1, a smooth map H to Y, such like H restricted to 0 gives you F, and H restricted to 1 gives you G. And a D-syn homotopy will be a smooth homotopy with an additional condition, which requires that the rank of H at every point of its domain is at most D. Or an alternative condition which is not equivalent, it's strictly stronger, but ultimately gives you similar answers at the end. Maybe another definition. So, or another definition, you can say H factors through some d-dimensional manifold. So dimension of W is equal to D. And of course, 2 implies 1. Because if you factor through a decomposition, so any map that lands inside a d-dimensional manifold has rank at most D, and the composition of two maps of rank at most D will have itself rank at most D. So this composition equals H, and H has rank at most D. The converse is false in general, but that's not really a serious issue. It's just changes some subtle aspects in the presentation, but ultimately it will give you similar answers. So, in the simplest example we illustrated here, this is a homotopy of a path, of a one-dimensional path of rank 2. Whereas here you see a homotopy of a one-dimensional path of rank 1. So we start at this path, and we deform it to a path like this, maybe. So a homotopy of rank 1 allows you to grow out these parts that stick out of the original path, but ultimately that's the only basically type of change you can make. And the basic property of parallel transport is that a parallel transport in any principal G bundle will be invariant under such homotopies. And ultimately, the reason for such invariance is that parallel transport is defined using integration of a certain pull. You pull back the connection 1 form and you integrate it. And if you pull back, so the curvature form is a 2 form. If you pull back the curvature 2 form along a homotopy of rank at most 1, it will pull back as a 0 form. And integrating a 0 form will always give you 0. And that's why arbitrary connections are invariant. The parallel transport is invariant under homotopies of rank at most 1, because pulling back the curvature 2 form of your connection along the homotopy of rank at most 1 always gives you a 0 form. This is ultimately basically the same reason why in flat connections you'll have invariance under arbitrary homotopies, because in a flat connection the curvature form is 0 And that always pulls back to the zero form. So in both cases, the reason for invariance is the same, is that the pullback of the curvature form along the homotopy is the zero form, and integrating a zero form gives you zero. But this zero form is achieved in two different fashions. For a flat connection is zero by definition. The curvature form is zero by definition. For a one single homotopy, pulling back a true form, a curvature true form along a one single homotopy will be a zero form because of the elementary properties of differential forms. But in either case, you get the corresponding invariance property. Okay, any more questions? Oh, by the way, if you're interested in an exposition for the one-dimensional case, I have I wrote a paper precisely about this a long time ago. It's called Smooth One-Dimensional. I think it was a topological field series. Or vector bundles with connection. This is joint work with Burke Evans. All right, any more questions?
You mean examples for D-thin gamatopy? Yes. One-dimensional. Or
Well, some examples I sort of gave you here. Maybe one canonical example is when I should have probably spelled it out more explicitly. Imagine you have a pass P in an arbitrary smooth manifold X. Then I claim there is a thin homotopy H from this pass to the identity pass. How does it work exactly? Well, it's really easy. H of x comma t will be by definition p of x comma t. Oh, sorry, p of x times t, sorry. So why is this thin homotopy? Because the multiplication map here, lands inside an interval 0, 1, which is then mapped to x using p. So that precisely means that the homotopy factors through a one-dimensional manifold. So pictorially, you start with a pass, and then you sort of start shrinking it like this. Eventually, you get to the point. So h of x comma 1 equals the original p, whereas h of x comma 0 equals, well, if you take t equals 0, this is just a constant passing p of 0.
Thank you.
Yeah. Yeah, there's also an interesting maybe variation on this. Imagine I took a path P and I glue it with this inverse. So I define maybe a map Q from 0 to X, where Q of T, Q of X, I should say, equals P of X if X is at most 1, or it will be P of 2 minus X for X at least 1. So pictorially, you have your original P, and Q, what it does, it first goes this way and then goes back using the same. So that's Q. Same path. Now, the nice property of Q is that Q of 0 equals Q of 2. So this is a loop. Q is a loop. You may ask, is this loop homotropic via a syn-homotropic to the constant loop? So notice the previous construction doesn't work anymore because this H, it does move the endpoint, right? So the endpoint, as you can see here, moves along the path. So I cannot just use this construction here to contract this loop to the identity loop. But there is a syn-homotropy that does exactly this. In fact, let me call it H. H will be a syn-homotropy of this form. How is H going to work? Well, H is going to use P and a certain, let's see, let me fix some parameter T and describe what happens when you fix T. So H of some arbitrary argument with some fixed T. How is it going to work? Well, this will be a map from this interval 0 to X. And the way it's going to work is you will apply some map from 0 to I guess 0, 1. And then you will apply P here. How is this map working? Well, let me draw the graph of this. Let's call it R. So here's a graph of R. So R, this is 0, this is 1, this is 2, this is 1. What R does, it will be identity up to a certain point, namely T. Then it will use a bump function to sort of become constant, stay constant. So this is point T. This will stay constant until roughly point 2 minus T. Then you will use another bump function to start decreasing toward 0. Yeah, and I guess now looking at this picture, I really should have parameterized using the interval 0, 1. So for t equals 1, you will see just this type of graph, which goes there and back again. So for t equals 1, h blank 1 equals q. Whereas for t equals 0, you will see the constant function 0, which means h blank 0 will be a constant function, which is just p of 0 or q of 0. And geometrically, this homotopy, what it does, it starts with the original loop, and then what it does, it will sort of make it shorter and shorter by stopping earlier and earlier and then going back. Like this. And you are welcome to check that this map, so this definition, of course, defines a map from this product to 0, 1, where here you apply P, and this is R. So R is defined for OT, so this gives you R as a map from the product. You are welcome to check that the rank of R is, rank of R by definition is at most 1. So that's why it's a thin homotopy. So that's a very, very typical example of a thin homotopy, and one that shows that its implication for parallel transport is that if you parallel transport along a path, and then you parallel transport along its inverse, you get identity. Okay, any more questions about thin homotropies and isotropies? Okay, that basically concludes our discussion of bordism categories. Well, there is one more proposition which I wanted to do. Maybe we'll do it next time. And it just illustrates something I previously mentioned about bordism categories, that all morphisms, except those at the very top level, will be dualizable. And all cylinders, meaning the product of a bordism and an interval, that will be invertible. And both of those facts require the presence of isotropies. And the proofs are very geometric. But perhaps we should discuss this next time, and this will be really the very last thing I mention about the bordism category. And after that, after we discuss this briefly, this proposition, we can finally give the ultimate definition of, in fact, which I can write right now, a d-dimensional functorial field theory with geometric structure S, which we can, in most general situation, take to be enriched. But also ordinary structures also work just fine because they can be promoted to enriched structures. So if you want an ordinary structure, that's fine, no problem. And category of values V is a morphism, or more generally a derived morphism. Let me remind you that a derived morphism was defined as a morphism, as an ordinary morphism from the cofibrant replacement to the fibrant replacement. In our case, all objects are cofibrant, so really what this amounts to is that you should perhaps replace V with a fibrant category. So let me put this in parentheses, so you can perhaps may want to require that V is fibrant, and if not, you want to fibrantly replace it, which will give you a correct notion. So maybe then I can erase derived is a morphism from the Bordism category with isotropies of dimension D and geometric structure S to V. And more generally, we will be interested in the whole space or smooth simplicial set, perhaps, of such morphisms. So this will be defined as a derived mapping object between two such objects, and this will be using the internal home, perhaps. So next time we'll be able to talk about this definition and immediately escape the main theorems, which is the locality theorem and the geometric cobordism hypothesis. And perhaps the next lecture could also be the last lecture, unless you guys have some explicit desires on what to do next. Like, I mean, if you really want to, I can also talk about the proof. I think the only somebody mentioned to me once, like, I guess she is not here today. Nivedika mentioned she is interested in the proof, but I haven't seen her for the last couple of lectures. So this is a question of whether she wants to still hear it or not. But
As I understand you, we will discuss in the next lecture about future additional lectures, yes? About
yeah. So if you guys have
some
any
cogomology, some elliptic cogomology, yes? Such
if you guys
topics,
have
yes.
any specific interests, yes, we can talk about what should be discussed. It's very much an open question. So what I'm saying is, like, next time I will state the main theorems, and from there we have a wide range of possibilities on what to do next. But perhaps we should be aiming to finish early May at the latest, because I will be traveling in May again one more time. So in mid-May, like third week of May, I will be traveling. So perhaps we should finish before that. So I probably will be, let's see. Yeah, we'll probably go traveling. So May 12th will already be difficult. So perhaps we should be aiming to make our last lecture May 5th. May 5th should perhaps be the very last lecture. So April 21st, we'll state the main theorems. And then we'll have maybe one or two more lectures, depending on your preferences, April 28th and May 5th, which we can discuss some material of your choice. And probably I should have also made some assignments, homework. Yeah, I wanted to do a second homework and third homework, but or perhaps we can also discuss solutions to the first homework, at least some of them, if that's your preference. So if you guys are interested in more homework, by the way, let me know. I'm happy to compose more problems.
I have a question.
Yeah.
Is there realization of the correspondence between Frobenius algebras and these functors from word V in this setting?
Yeah. So of course, if you take, Frobenius algebras basically arise from, oriented. The GCH will imply that if you take your geometric structure S could be orientation, so D equals true, S equals orientation. Then the GCH will imply as a very special case of GCH, you will see the two-dimensional functorial field series with orientation through the category of algebras, bimodules, intertwiners. These are in bijection with their values at a point which will be a separable Frobenius algebra. Separable Frobenius algebra. And what's called A. And then if you are interested in traditional topological field series, which are just functors from one-dimensional Bordisms and one-dimensional manifolds and two-dimensional Bordisms between them, then the value on a circle for such a field series F, so F evaluated as a circle, will be the center of A, which will be a commutative Frobenius algebra. And that's how you see the traditional result about the classification of just ordinary two-dimensional TFTs, non-extended. So that's the this ties in with the classical result. By the way, I should mention this probably first was observed by Christian Marquez. His PhD thesis is about Frobenius algebra. This is about 2009. But let me also point out that GCH also allows you to go way, way further. For example, it will also immediately tell you, immediately yield similar classification where algebras are replaced with, say, DG algebras. And the advantage of this is there are many more dualizable DG algebras, fully dualizable DG algebras, than there are separable Frobenius algebras. So you get a much more interesting result this way. And this is something that actually requires much more of the power of GCH, because for DG algebras, that means you have an infinity true category as your target, and that's not covered by the existing classical write-ups. I'm not sure if anybody already figured out what the fully realizable DG algebras are. I may have seen it somewhere. It's a good question. I'm not totally certain, but in any case, that could be a new result that is not implied by the previous results. Yep.
And so what about some higher structures or algebra structures in this setting?
Higher structures on what?
I mean the applications of high algebra structures like operas, so on.
Well, operas can enter in many ways, but the one point perhaps is that any functorial field series, say dimension 2, for example, gives rise to an algebra or even more generally, in any dimension, you get an automatically from if you have F, a functorial field theory, board D with some geometric structure S to some V, you get what is called an algebra over the little disks operag. In our case, it will also have a geometric structure S. So in particular, you do recover the traditional setting. How does it work? It's actually extremely stupid. The underlying object will be the value of F on a sphere of dimension D minus 1. And then if you have a morphism in the little disks operag, so how does a morphism look like? Well, in say D equals 2, for example, a morphism looks like a bunch of disks inside of another disk. Right. And look closely at this picture. What do you see here? You see a bordism from 3 circles to a single circle. And you can evaluate F on this bordism. And this gives you precisely the structure morphism for the corresponding algebra over the little disks operag. And in this manner, you can extract an algebra over the little disks operag from any functorial field theory.
Okay, thank you.
Yeah, so it's I don't think anybody wrote it up in full generality actually, but that's one of the basic correspondences between functorial field series and algebras over little disks opera. Yeah, and this is of course will be tied into factorization algebras and factorization homology. So there are many interesting connections here to explore. Yeah. Any more questions? All right, then I guess that's it for today, and I'll see you next week.
Bye.
Okay, have a nice day, guys.
Thank you. Bye.
Goodbye.
Bye.